Previously, we've been looking at systems with a single optical element, such as a lens or a mirror. Here we're going to go and take a look at what happens if you have more than one element in the system. So what I have drawn here is a two-lens system. The first lens is a converging lens of focal length plus 5 centimeters. And the second lens is a diverging lens of focal length negative 8 centimeters. And what I'd like to do is locate the final image of and try to figure out what its magnification is. So my object here has a height of 1 centimeter, and it is located at 4 centimeters inside the, at 4 centimeters away from the principal plane. So you should pause for just a second and ask yourself, is this just this lens right here? Would this be a case 1, 2, 3, or 4 situation? Okay, it's a case 3 situation, which is a converging lens where the object is inside the focal point. And we know that the image you have will be virtual, upright, and magnified. Now it'll turn out that what we'll do is we'll go ahead and locate the image for this first lens. Once we locate it, the rule is, and I'll justify it after we do the example, the rule is that you use the image from the first lens as the object for the second lens. So let's go ahead and start drawing our ray diagram. So we'll go ahead and start with the paraxial ray. So it will go and deflect out through the focal point. And you'll notice here I'm trying to keep my rays kind of short and tidy, because otherwise this is apt to turn into a real mess. Okay, then we'll go ahead and do the focal ray. That would be the ray that is aimed from the focal point, like so. Hits the, whoops, wrong color. There we go. So that would be the ray coming from the focal point, goes to the principal plane, comes out parallel. Okay, we can already look at these to see that they're going to be diverging. This will indeed have our virtual image. But let's go ahead and draw our truest, bestest friend, the central ray, just to help us locate the image. Okay. So the recipe says that we need to backtrack these rays. So let's go ahead and backtrack it. It's pretty good right there. Oops. Sorry. Go ahead and backtrack the ray. Dashed line. That's pretty good. We'll backtrack that one. And we'll backtrack that one. Okay, so we've located our image. It is right here, and this virtual image is indeed virtual, virtual, upright, and magnified as advertised. All right. So now what you do is you go ahead and now you pretend that the first lens never existed and that the object is just plain located where this intermediate image is. Oops, sorry about that. There we go. So, and our lenses here are 12 centimeters apart. So what we'll go ahead and do is we'll go ahead and do the paraxial ray again. This time I will do it in a different shade here. You'll see, and this is not a coincidence. Oops, if I do it right, that is. There we go. You'll see, and this is not a coincidence, that lies right over the ray we just backtracked. And now, since this is a diverging lens, it is going to bend away from the focal point of the second lens. All right. And similarly, we can go ahead and find our new focal ray. So we'll do it in a light blue. So this is the ray that's going to be aimed at the focal point. And keep in mind the rules of the focal points are reversed when you have a diverging lens. And that ray will go out parallel. And then finally, our truest, bestest friend is the central ray. So I'll go with as close as I can do to a toned down orange. And that's just going to shoot through undeflected. Okay. So my central ray is already backtracking itself. That's good. So I just need to go and backtrack the other rays. Not too bad. And looks like our image is probably about the roughly-ish the same height we started. We'll have to do the math to know for sure. But it's virtual, upright, and minified. So a virtual image can be used as the object for the next lens. That's not a problem. And we could have even made a real image of an object that was itself a virtual image from something else. That's not a problem either. So what is up with this identifying the, oops, sorry about that. What is up with this using the intermediate image? Well, what it's really doing, and this is how I can justify this after the fact, is what this is really doing is it is identifying the rays that we needed in order to be the special rays for the next lens. So really, this ray here did not originate back at the intermediate image. It originated at the object, like so, and then refracted down at the principal plane. And same with this central ray here. It also really originated here and refracted down. So this intermediate image business is just really a trick to help us find the special rays we need for the next lens. And if you had, say, 3 or 4, 27 lenses in a row, you just keep the process up. Then the rule is always the image of the first is the object for the second, and so forth. Okay, so with that, let's go ahead and start locating our images. So we can say for anything that, oops, 1 over dO plus 1 over di equals 1 over f. So we can locate our image. And we'll say that di, oops, my bad, 1 over di is equal to 1 over f minus 1 over dO. We'll go ahead and put things on a common denominator and say this dO minus f over dO f. There we go. And then you can flip it. So in the case of our first lens here, we can say that di1 will be equal to do1 f1 over do1 minus f1. do1 we said was 4 centimeters. f1 is 5 centimeters over 4 centimeters minus 5 centimeters. So this intermediate image is located at negative 20 centimeters. Now we got to be super duper careful here. And it's very important when you do these multi-lens systems. As you keep figuring out distances, keep dimensioning them. So here is my di1. It's equal to negative 20 centimeters. The negative sign just means you're on the wrong side of the lens versus the light. Excuse me. And however, that is not going to be the object distance for the second lens. The object distance for the second lens is going to be this distance here. So DO2. It's going to be this distance L minus the image distance, because we know it's got to be more than 20 centimeters, right? It's going to be 32. So it's L minus DI1. So this is 20 centimeters minus a 12 centimeters minus a negative 20 centimeters equals 32 centimeters. And that is positive because the object is located in front of the lens. Now, the beauty of doing this symbolically here is that to locate the second image, we can just plain recycle the result. So now I just change all my 1 subscripts to 2's, and I'm done. This is literally the same thing. So we put in our new values. So we said that DO2 was 32 centimeters. And F2 is negative 8 centimeters. And this is going to be 32 centimeters minus a negative 8 centimeters. That works out to be negative 6.4 centimeters. From where? From the second lens. So we've located DI to here. Alrighty. So now with all of that, we can figure out what our final image height is. So we already know the height for the object, right? HO1 here was plus 1 centimeter. So from the magnification relationship, the height of the image, HI1, is going to be equal to minus DI1 over DO1 H1, HO1. So this will be minus a negative 20 centimeters over the object distance was 4 centimeters times 1 centimeter. So we get that our intermediate image is 5 centimeters high. Well, and it's positive, so it tells us it's upright. But, I'm sorry, that's HI1 there. Now, HI2 is going to equal minus DI2 over DO2 HO2, but HO2 is the same thing as HI1 because the image of the first thing is the object for the second. So we can go ahead and put in our numbers. This will be negative 6.4 centimeters over 32 centimeters times 5 centimeters. This works out to be a fifth. So at the end of the day, all this thing did was bring the image closer to your eye, which isn't necessarily a bad thing, because although that didn't change the lateral magnification one whit, it is taking up a bigger angle in your eye, so we would say that it increased the angular magnification. Okay, and before I leave this here, I will throw in one other little result. I will define a quantity called the refractive power of a lens. The refractive power is defined to be 1 over the focal length. And usually the unit used is the diopter. And this is an inverse meter. So if your eyeglass prescription is, say, negative 0.5 diopters, it means you have a diverging lens with a negative 2 meter focal length. Well, it turns out that if you have two lenses in contact, the refractive power of the combination is equal to the sum of the refractive powers, which is why opticians like that. So this is why you tend to see it for eyeglass and contact lens prescriptions. Okay, in the next video we will take a quick look at cameras and then see how an eye is and isn't like a camera.